So I want everyone to go to the search bar in their computer. You can just type in R, and then one of the first apps should come up is RStudio, or you might have to type the whole thing out. But we can go ahead and open up RStudio. Basically, this is what the RStudio window looks like. So when you first open it, it might ask you to choose default R version. You can just leave that on default because you should have 4.4.1 installed. You'll see the R version here. So we have different windows. This window here to the top left is what we call the code window. And so this is where all the code will display. Down in the bottom left, we have what we call the console. Down here, messages will display as we're running our code, and we can also directly enter code into the console as well. In the top right, we have our environment window. As we're running the code and building data objects, we can use this to pull up views of the different data objects. And in the bottom right, we have different windows that we can look through here. You can click and then set it to files, and then so all of the files in your current environment will show up, allowing for easy access. But so I want you to go ahead and close down RStudio. And now all of you should have gotten an email from Talyia with a link to the GitHub repository. So I'm just going to pull that up here. So if you've already gotten the files downloaded, you can just follow along. But so for those of you that haven't downloaded the workshop files yet, you can go to the link that Talyia sent. So if you go to that link, it's hopefully not broken. It'll pull up the correct GitHub repository. And so to download the workshop files, we can go to where it says releases on the right side and click on workshop files. And then we can click on source code, which will start downloading a zip file of our source code. And for easy access for this workshop, we can just go and download it right to the desktop. And so we have our zip file here on the desktop. So if you're using a Mac, it might automatically extract it for you. On Windows, you'll have to right click and then go and click on extract all, and then click extract, and it'll extract it all to a new folder, and it should automatically open up for you. So we can go into the workshop folder, and we have all of our different files in here. So the first thing I want everyone to do is find the spatial reg workshop file. That's a RMD file. So this is what we call an R markdown file. This is going to have all of our R code. So we can right click and then go to open with, and then use RStudio. It should show up as an option. And then so when you open it up, the code will appear in the top left code window here. And so this is called an R markdown file. And basically it's kind of, you can think of it as like a notebook extension of a normal R file, where we can have different types of text describing our code. And then we can have, basically we can have what we call code chunks, where we can have little individual chunks of code that we can run, and then run through that without having to run through the entire R code all at once, which just makes debugging easier and doing different types of analysis and things like that. And so included, if we go back to the workshop files folder, included with that, we have another spatial reg workshop file that under type, you'll see it's a HTML document. So you can just go ahead and double click on that to open it, and it should open in your internet browser. And this is a compiled HTML version of that entire R markdown code. So it has all the same text and everything. Just looks a lot nicer. And then here you can see we have all the code from the chunks, and then it also shows the output from each code chunk already fully rendered in there. So you can follow along with this document. It's a great way to share code. You can use it if you get behind or get stuck. For those of you that are experienced with R, if you want, feel free to work ahead, use this as a guide, experiment with different things. You'll notice in the code chunks, there's comments for different things to try out if you're feeling confident or want to experiment. But for the workshop, I'm just going to go through this, and we can all go through it together. Yeah, so before we get started on actual code and stuff, I'll just go back to the slides and we can just go through a brief background on the concepts behind this workshop. So again, in this workshop, you're going to be introduced to open source GIS using R, as well as techniques for leveraging GIS tools in spatial data in the context of health science. So really, we're going to introduce you to the fundamentals of GIS data structures, loading and visualizing spatial data, spatial relationships, and doing a regression analysis in R, both normal linear regression and spatial regressions. And so this is really just, it's again meant to be an introduction, how to do spatial statistics in R, and then really provide you guys with a code base and the initial skills that you can use to take to your own research. So for our analysis, we're going to be performing geospatial data science in what we call a Geographic Information System, or GIS environment. And so GIS is basically a computer system that analyzes and displays geographically referenced information. So in other words, it allows us to incorporate location into our data analysis. And then we're going to be performing this data in R, which is an open source coding platform for data analysis. And R allows for more effective work as a researcher, allows you to automate different tasks, enhances collaboration, and it's really good for making your methods reproducible. If you have R code for your whole analysis, you can share that with somebody. They can run it on the same data and get the exact same result as you did. So in this analysis, we're going to construct what we call geospatial models. And so geospatial models are like normal statistical models with the additional assumption that there are spatial patterns in the data and that the locations of our observations can uncover relationships that may otherwise go missed. So we're going to explore the differences between what we call global and non-spatial global models and spatial local models. So in the context of geospatial analysis, what we mean by a global model is a model that's not directly or explicitly accounting for spatial relationships. So in other words, all observations have equal weight in the model, no matter their location. But in local models, we're considering these spatial relationships between variables across localized areas of the study extent. And so we call these localized areas neighborhoods. And local models are assuming that relationships between the predictor and outcome variables can vary across space and time. So this allows us to model processes that may vary over space with greater accuracy. So I'll also mention that you're gonna, we call these neighborhoods, but you'll hear neighborhoods referred to as kernels. This is just one of the many confusing things out there. These are kind of used interchangeably. You can basically think that all neighborhoods are a kernel, but not all kernels are neighborhoods. But you'll see those used interchangeably in this type of analysis. And so local modeling is especially valuable in the realm of public health, in which, the associations between an environmental exposure and a human outcome is often represented as a very complex, nonlinear, and spatially heterogeneous relationship. So geographically weighted regression, or GWR, is a commonly used example of a local spatial regression technique. So GWR models spatial processes by evaluating a local regression equation for every neighborhood. So it allows for variance in the relationship between variables across the study extent. And for a more complex example, we have what we call a multi-scale GWR, MGWR. And so MGWR allows for expanded dimensionality in analyzing the spatial relationships in which the neighborhood can also vary in size. And so this is what we call an adaptive kernel or an adaptive neighborhood. And I'll also mention you'll also see neighborhood size, this adaptive neighborhood size. You'll see that often referred to as the bandwidth size as well. So just another term to throw out there. But for our analysis in this workshop, we're going to use GWR as our spatial modeling approach. I just want to mention that there's several other spatial modeling approaches out there, such as machine learning driven methods. So the basis of spatial analysis is this concept that we call spatial autocorrelation. So spatial autocorrelation is basically the assumption that data from locations close together are more likely to be similar than data from locations farther apart. As geographers, we refer to this as Tobler's law, known as that everything's related to everything else, but things that are near to each other are more related than distant things. So while spatial autocorrelation is a fundamental basis of spatial analysis, it's also a double-edged sword. So while we assume that our raw data as a geographer is going to be spatially autocorrelated, spatial autocorrelation in the residuals of our models is basically indicating that our model is poorly specified. And this is something you'll see in the workshop, in which a model that has spatially autocorrelated residuals is indicating that it's missing, or it's not representing a lurking spatial variable very well. And so in this workshop, you're going to see basically how we see a lot of spatial autocorrelation in a linear global model, and then how using these the geographically weighted regression, we can reduce the spatial autocorrelation in the residuals and create a better specified model. So in this workshop, we're going to examine how rates of low weight births, which I'll refer to as LWB in Colorado, relate to environmental pollution and socioeconomic covariates. So our main objective is to basically demonstrate how spatial relationships may be lurking variables in regression models. And so using this data, we're going to model the relationship between low weight births and environmental pollution corrected for social vulnerability variables. And we're going to first start with an ordinary least squares linear model, our global regression, and then do a geographically weighted regression, our local spatial regression. And then if there's time, we can also show the multi-scale geographically weighted regression, how that's the most optimal for capturing these spatial relationships. And then throughout the workshop, we're going to learn how in R to assess the strength and predictive capability of our model, look at model residuals, and test for spatial autocorrelation. And so we're using various data sets. For our exposure variable, we're using something called the Toxic Release Inventory, or TRI. And so this is a measurement of the average total releases in pounds within 50 kilometers of populated weighted census tract centroids. And all of these links can take you to more information on the data, and we'll share these slides with you after the workshop. Our covariates are going to be from the CDC Social Vulnerability Index, which I'll refer to as SVI. We're going to be looking at a different demographic, household characteristics, different themes as our covariates in the model. And then our outcome variable is going to be rates of low weight births, LWB, from the Colorado Department of Public Health and Environment. And so you're going to be introduced to, again, first reading in data in R, manipulating and engineering data in R, projecting data spatially, spatial statistics, data visualization. And since I'm a geographer, we're definitely going to make maps as well, which we always say is the most important form of data visualization. I'm just going to go through now the very basic fundamental R operators. So again, R is an open source scripting language for data manipulation and analysis. So first we have our most basic, the variable. So in R, we define data objects such as a spreadsheet of our SVI data as a variable. And so variables allow us to easily reference complex data objects. So instead of, say, having to read in our data table over and over again, we can assign it to a variable, and then whenever we reference that variable, R will know that we want to look at that specific data table. You'll see $ in the code. This is what we call extractor operators. And so this is used to reference specific variables in a data table or object. So again, if we have like a spreadsheet of data, we'd use the extractor operator to say, I want to look at the specific column or the specific variable from the data table. This left arrow dash is what we call the assignment operator. And this can kind of be thought of as an equal sign in R. And we use the assignment operator to define variables. Next, we have what we call the pipe operator, which is this percent, right arrow percent. And so this is a way to chain operations together, i.e. pipe information, why they call it the pipe. And so basically it'll take the output from the left side of the pipe and pass it to an expression or function on the right. So for example, we can use the pipe to take like a data object represented by the variable and pipe this into whatever function we'd like to use. And then lastly, we have the data frame. So basically, you can just think of these as data tables. In R, we refer to these as data frames. And so these are data objects that act like an Excel spreadsheet in which columns are variables and fields, and then the rows are individual data observations. And so lastly, I'm going to go over the data, a shapefile. So there's many different types of geographic data types. For this workshop, we're just going to focus on this, the shapefile, which is it's a data format for storing geometry and attribute information of a spatial data set. So we can all go back to the workshop folder. And then I'm just going to quickly show under the folder tracks, this is where we have our spatial data. And so what we call shapefile is this .shp. And then there are 5 other subfiles associated with the shapefile. And I won't get into the nitty gritty here about what these do, but basically all these different files tell our GIS environment how to draw the data, where to draw it on the surface of the earth and stuff like that. But so you only need to worry about this .shp file. And then when you reference it in R, as long as all these files are in the same folder, R will know to look for those automatically. So we can go back to RStudio and we can start working through the code. In our R Markdown file, we have basically background information describing exactly what I went through on the slides, so you can go back and reference that in the future. But so I want everybody to scroll down, and we're going to start on line 150, which is a step 0 loading libraries into an R environment. And so basically in R, we install packages into the environment. And so on everybody's if you're all working on the desktop, your packages should already be installed. All right, so for those of you that already have your packages installed, I want you to go to step 0, where we're loading in libraries. And so when we install our package, after we install packages into our environment, we have to load them into our current working environment so we can reference them. And so we'll run the first code chunk here. So you can see basically this grayed out area. I want you to go to the top right corner where you'll see a green arrow and click that to run the current chunk. And it'll take a couple minutes, or not a couple minutes, but a little bit of time depending on your computer. And so when it's done running, in the console at the bottom, we should have this right arrow with our cursor with nothing there. Display some messages under it. We can scroll down to the next step, which is step 1 on line 196. And so this is where we're going to actually start reading in our data. So you can see on line 202, we have this variable dat underscore tracks, and we use the assignment operator to assign it the shapefile of our census tract data. So we use this function called st underscore read, and we're telling it to read in our tract shapefile, and we're going to assign it to that variable dat tracks. And so one thing I can show you is if you Google just st underscore read with the parentheses, the first link that should come up is the R documentation on that. So pretty much every function in R, you can easily Google it like this, and then go to the documentation which describes how the function works, all of the different arguments that you can have for it. And so here we're using just the default arguments, but you can look for any R function to see detailed descriptions of everything. And like you can see that DSN is that data source name. So back in the code, we're saying our data source name is equal to our shapefile and reading it in. And then lines 205 and 206, we're just plotting out those shapefiles to make sure they're read in correctly. So we can go to the green arrow in the top right corner for this chunk and run current chunk. And then if it runs properly, it should display a shapefile showing all of the census tracts in the state of Colorado. So this is our basically empty spatial data. These are just polygon files representing the census tracts. And what we're going to do is we're going to take all of our data, our exposure data, our covariates, our outcome, low birth weight data, and join that to these census tracts. So we can all go to the next step, step 2, import exposure data on line 211. And here we're going to read in our exposure data and define it as a variable DAT underscore TRI. So again, this is a toxic release inventory data. And we're using this read CSV function. This is how you read in like raw spreadsheet data. And what we're going to do on line 218, we're going to use the extractor operator to pull up data for the GeoID 10 field. And so what this field is it's called a GeoID. And so each census tract has a unique GeoID number that allows us to identify what that census tract is. And what we want to do is we want to make sure that all of the GeoIDs are the correct length, because sometimes there can be error in data, especially some census tracts, their IDs start with zeros, and sometimes the zeros get cut out. So what we do is we assign this function to the GeoID 10 field, where we're going to pad the GeoID with zeros to the left side until the length is 11, which is the standard length of the GeoID. And then on line 220, we call this function called unique, and we're telling it we want to see how many unique characters are in the GeoID field from our dat underscore try variable. And so that'll tell us if all the fields are length 11, which is what we want. So we can go ahead and run this chunk again by clicking the green arrow. And then it outputs 11, showing us that the code works properly. Now we can see in our environments that we have our track shapefile and we have our TRI data. And you can click on the TRI data to open the actual data frame, and you can see it looks like a spreadsheet. And so each row is a unique census tract with its GeoID and the average releases of emissions over the past 10 years assigned to each census tract. And all of our GeoIDs are the 11 characters long that we want. So now we can go to step 3, which starts on line 224. And this is where we're going to basically do the same thing. And now we're going to read in our SVI data, those social vulnerability, different demographic information. So we're looking at things like socioeconomic status, household characteristics, minority status, and housing type and transportation, and using these as covariates in our model that might help explain the distribution of low weight births. So again, we're using that read CSV to read in our SVI data the same way. And we're going to do we're going to pad it and make sure that the GeoID is 11 characters long. You'll see for the SVI, we're using a field called FIPS. And so this is something kind of annoying in census and government data. You'll often see FIPS and GeoID used interchangeably. That is technically incorrect. So FIPS stands for the Federal Information Processing Series, and these are 5-digit county subdivisions, but people often will just use FIPS in place of GeoID. So just like in your own research when working with census data and stuff like that, sometimes you'll see FIPS, sometimes you'll see GeoID. They're usually the same thing. But if you see FIPS and it's not 11 characters long, then they're using it correctly, and that's not a GeoID. And so in this code, on line 257, we're going to create another variable called SVI underscore sub. And we're going to use the pipe operator to create a subset of the data, because this raw SVI data, it's for the entire US, and we only want stuff for the census tracts in Colorado. So we have this, we're basically piping in our SVI data into a filter function that is looking only for records that are assigned to Colorado. And then another thing we're going to do is we're going to have to deal with missing data, because this is a very big data set. There's a lot of census tracts where there is no data for that particular tract. And so the SVI database, they use the negative 999 to indicate a missing record. We need to deal with that, because if we leave it like that, R is not going to know it's missing, and that'll mess with our statistical analysis. So what we need to do is replace all these negative 999s with NA, which is R's version of a null value, and that'll tell R to ignore those missing records, and we can deal with that later. And then we're also going to do a final pipe function, because this SVI data set has tons of variables besides low birth weight. We only want to look, or besides, or it has a ton of different demographic variables and things like that. We're going to pipe our SVI sub into the selection function, looking for variables that only start with RPL theme, which is the theme variables we want. And then again, we're going to check the length of the unique characters. So we can go ahead and run this code chunk. And it'll take a little bit of time depending on the hardware in your computer. Again, so once it runs through in the console, you'll see that arrow with our blank cursor. And then again, we're seeing that we're getting 11s, meaning everything's the right length. So again, if you go to your environment, we can kind of look at it and see what we did. So we can open the original SVI, and we see it's a big table. We have information from states like Alabama that isn't Colorado, with just tons of information in it that we don't need for our analysis. And then so after we do our filtering functions and we get our SVI subvariable, you can see we're left with the FIPS, which is our census tract identifier, and then the different theme variables that we want to use in this analysis, and nothing else. Now we can go down to the step 4, which starts on line 273. And now this is where we're going to read in our outcome variable, which is our low birth weight data. So we do the same thing again, where we're reading in the CSV for our health data. And then we're going to create a new variable called LWB for low birth weight. Again, because our health data set has tons of variables. It has things like asthma and other health effects that we're not going to look at. So for this new variable LWB, we assign it as our full data set outcome, wherein we're telling it that we only want columns 2, which is our GeoID, and then also columns 26 to 32, which only has to do with low birth weight data. And then so after we get a new data set with just the columns we want, we again do the padding of the FIPS variable to make sure it's the right length. So we can go ahead and run this code chunk. We get 11. And then we can look in the environment to see what's happening again. So if you open the outcome, again, you can see that we have a bunch of different variables like asthma and different things, diabetes, that we're not going to need in this analysis. And so we did our selection and assigned that as a new variable, which outputs just data table, again, with the GeoID or FIPS code, and then just variables of a low weight birth that we want to look at in this analysis. Now we're on step 5, which starts on line 290, where we're going to combine the data tables. So we have a separate data table or data frame of our data. We have our census tracts, we have our exposure data, we have our covariates, and then we have our birth weight data. Is all separate data tables, and we need to combine these into a single table so we can input it into our statistical functions later on. And so the first thing we're going to do is we need to take our spatial data that dat underscore tracks, and we're gonna assign it as a new variable called dat underscore full, and we're going to use this st as sf function, which is basically taking our spatial data and turning it into a normal data frame without the location information, because in R we can't directly combine a non-spatial data to spatial data. So we're going to first convert everything to non-spatial data, join everything together, and then turn it back into spatial data. And so we join our all of our data to dat full by using a series of right joins. And so basically what this is doing, it's looking for each data table. It's going to match each row based on the GeoID, and then it's going to add that data in from the table we're joining as a new column to the right side of the data set. Then we're going to create a subset of our dat full to input into our global models using only certain variables that we want. So we only want a GeoID. We just want our average releases, which is our exposure. We want our low weight berths. And then we just want the variables starting with RPL, which will select the right theme variables that we want. And then lastly, everything's joined together. We're going to have to reconvert everything back to spatial data. So we do this in line 324, where we're basically overwriting our dat full variable. So we're saying we want dat full to now be assigned to dat full with the NAs emitted. So this is where we can drop all of the null data. So it's going to drop census tracts that don't have data. And then we're going to put that into an as function, and we're saying we want it as spatial. So we're going to turn dat full back into spatial data and drop all the census tracts that don't have data assigned to it. And then lastly, on line 326, we run a summary function of dat full, which will put out basically a summary readout of the data in our full data frame to make sure everything ran correctly. So we can go ahead and run this code chunk. And so you'll see that out under the code chunk is outputting a summary of our data. And now we can see that we have all of our data combined together. We have our low birth weight data, we have our exposure data, and we have our different themes representing our socioeconomic covariates. And so this summary tool is just a great tool to use. So like any spreadsheet of data that you feed into it, it'll output a summary like this, not only with the variable names and the data type, but if it's numeric data, it'll automatically generate the full interquartile range for each variable. So you can easily get the mean value, the minimum, max value, and different things for all the variables in your data set. Moving on. So we have all of our data joined and formatted together, and now we can actually start doing some diagnostics. So the first thing we're going to do is we're going to put this into a correlation matrix function. So basically what this is going to do is going to make scatter plots of the correlation between every single variable and every other variable. So it's going to be like, all right, we're going to look at our average releases against our low birth weight. On the x-axis, we're going to have the value of low birth weight. On the y, we're going to have the exposure level. On the y, we're going to have the low birth weight, and it's going to have a point everywhere. So for every row, it's like, what is the pounds released? What is the low birth weight value? Is going to draw a point there. So we can run this code. And this one might take a little bit of time. So what it does is it outputs our correlation matrix. And so depending on your computer and the hardware, RStudio can get kind of clunky in markdown files where it doesn't display the full image as you can see here. So if it's cut off for you, you can go into the output. There's this little symbol in the top right, the symbol all the way to the left, which is show a new window. It'll open the display in the new window, and then you can maximize that new window, and it might for you show the whole thing. It might still be cut off like it is for me. And if it is still like that, then we can right click the output, do save image as, and we can just save this right into the desktop. And then so it's going to have this weird extension on the file type. We can delete everything besides the .png, and then we can hit save, and that'll output it as an image. And so if we go under our files in RStudio, we have our file tree here. We can go to desktop to easily find things, and we can find that image that we just output, which is a bunch of zeros, 10.png. We can open that, and then now it's displaying correctly. And so this is the correlation matrix here. So basically what this is doing a pairwise comparison between every single variable. So like we can look at our exposure, average releases in pounds over the 10 years. And then so this square here is that exposure variable compared to the low weight birth. And then it's like theme 1 compared to low weight birth and so on. And so the x-axis is the average releases, the y-axis is the value of the low weight birth, and then it's drawing how all those basically output points look. And so you can see that there's some evidence of linear trends in certain things. Some of our data is normally distributed, some of it is very skewed. And so basically what this is all telling us is there's trends in the data, but there's a lot of variance going on in the data, and definitely not direct linear relationships between everything. And so now we can go down to step 6 on line 369, which is where we're going to start with our linear model. So we're going to run a linear model. Basically, we're going to call this function LM, which is a linear regression model in R. And again, as a reminder, you can just like Google LM parentheses, and then the first thing that's going to come up is the documentation for the linear models in R. And it gives, again, details on all the different arguments and stuff like that. I'm not going to get into the gritty nitty for this workshop here, but you can reference that if you want to learn more. But so we're calling this function, and then so in the arguments of the function within the parentheses, we're saying that our dependent variable is going to be the low weight birth. And then we use this symbol that we refer to as a tide. And so basically in R, this is you use this to assign relationships between variables. So we have our dependent variable on the left, and then on the right, we have all of our explanatory variables. So our exposure variable, and then the different covariates that are the themes. And then our last argument, we tell R what data we want to use to run our linear model on, and we're assigning it to our global dat variable, which is just the fully joined data table of non-spatial data, because we're doing just a linear regression that doesn't consider spatial location. And we're assigning the output of this linear model to a variable called lmfull. So then going forward, we can reference this variable, like putting into a summary function, which will display the results of the linear model. So we can go ahead and run this code chunk, and the linear model should run pretty quickly. And then so the output below the code chunk will be the results of our model. We can see all of our variables and the regression coefficients. Some of these variables are significant. And then down at the bottom, we can see our global statistics. We have a significant p-value. And then we can see our adjusted R squared, which is pretty low. We're just getting a 0.109. So not a very well fit linear model. So we can start looking at some model diagnostics to try to see what's going on. So we can move on to step 7, starting on line 381. We're going to interpret the global model. So the first thing we want to do is we want to look at the normality of the residuals. And we can do that with a QQ plot. So basically in this code chunk, we use a QQ plot function. And this allows us to do a plot of the residuals. And we can go ahead and run that code chunk here, and it will output the QQ plot. And so again, I'm just going to do the save image as, because on your computer, it might display everything fully correctly, but mine, it's having problems. So I'm just going to save it as an image. So it shows up in our file tree. We see the full QQ plot here. And so this is showing the residuals of the regression analysis. So basically the difference between the actual value and what the model is predicting. And so if we had a well-fit model, we'd want all the residuals to be normally distributed. So we don't want them all to fall into this blue confidence interval. But we can see there's a significant amount of outliers. And so each one of these circles is representing a particular census tract. And at these particular census tracts, the model is not very well predicting what the actual low birth weight is. There's a very big difference between what the model predicts and what our actual health data is showing, indicating that the model is not capturing all the relationships. And so we're assuming that this linear model is not modeling lurking spatial variables. And so we can investigate that by testing for spatial autocorrelation. And so we do this starting at line 404. And we're going to use a test called Moran's I that tests for spatial autocorrelation in the residuals. And so what this test does basically, it looks to see if the residuals are spatially autocorrelated or not. And so if the results of the test are significant, that'll mean we have spatially autocorrelated residuals, indicating that the model is not capturing those lurking spatial variables. So we can go ahead and run this code chunk. And so once it runs, you'll see the statistics output. And you can see that the p-value of Moran's I is very significant. It's reporting 0. So that means we have highly spatially autocorrelated residuals, and this is indicating to us that the model is not capturing lurking spatial relationships. So now we're going to move on to our local spatial regression models, starting on step 8 at line 432. So we're going to start with the GWR and R. And so the first thing we need to do is we need to calculate what we call a distance matrix. And so a distance matrix is basically just a measure of the distances between the locations of all the observations in our data table. And this matrix will allow the GWR function to have an understanding of the spatial variance across our study extent. And we're doing that with this gw.dist function. And we input our dat full variable into that. And we assign it this variable called dm that we can use to reference later on and pass to the full GWR function. So we can run this code chunk. And nothing will show from there, but you'll see it show up in your environments. And so this is a large matrix of a lot of elements representing all of basically the distance from every point to every other point. And then the next step in step 9, starting on line 444, is we need to compute bandwidths. So if you remember from the background presentation, bandwidth basically just means the size of the neighborhood. And so we run this bw.gwr function on our data set. And we're using basically this automated cross-validation method where it optimizes the neighborhood size based on that distance matrix. And so we can run this code chunk. And so it starts running and we'll see it's testing different bandwidths or different neighborhood sizes. And it outputs a score for that. And then so it'll use the most optimal neighborhood size based on how it ran through. And so again, you can go to the documentation to see what all these different attributes mean. We're using basically standard settings for the GWR, but depending on your own data set and your own use case, you can use different attributes for all these different things and different approaches. But so this is a very basically standard and common way to approach things. And so now in step 10, starting on line 464, we're actually going to run the GWR. So we're just running a gwr.basic. And so again, we're using our tide to tell it what we want our dependent variable to be, what we want our explanatory variables to be, we want our data set, and then we're going to assign our bandwidth that we optimized. We're going to assign our distance matrix. And then we basically call the variable to output all the results from a GWR model. So we can go ahead and run this code chunk. And it's going to output similar to a linear model, but there's a lot more information from the GWR. We can scroll through all of this. And then on step 11, starting on line 485, we can use our extractor on the GWR results variable to extract what we call a gw.diagnostic. And so this will just tell us the main diagnostic information that we want in a clean format. So you can run this code chunk here. And so this is going to output different things like the AIC criterion. But what we're most interested in for this workshop is just the adjusted R squared. And so as you can see, the adjusted R squared has increased, still pretty low. But basically, the GWR is capturing the spatial relationships in the data better than the linear model did. And we're seeing that with the increased R squared value. So we can look at the same diagnostics as we did before, like the QQ plot on line 497. So we can run this code chunk. And we see the QQ plot here again. Looks pretty similar. So we didn't improve the residuals all that much. And starting on line 502, we can do our spatial autocorrelation test again. So we can run this code chunk here. And so the values that you see here specifically might vary a little bit because there's an inherent randomness to the spatial autocorrelation test. So again, we still get a significant p-value. So we're still having spatially autocorrelated residuals. And so the normal GWR is not capturing all the spatial variance in the data. What we do see is that the Moran's I statistic is smaller. So that means that things are relatively less spatially autocorrelated. So we can assume that the GWR is capturing these spatial relationships a little bit better than the linear model. But there's still some work to go. So we can keep looking at some different diagnostics of the GWR. So one benefit of the GWR, again, is that it is a local model. So we can look at, for every single census tract, different attributes. So starting on line 520, we're going to plot the distribution of beta coefficients. And so what this is going to do is basically we're going to see for every single variable, we're going to see the distribution of the coefficient value across all the census tracts. And to do that, we start on line 529. We're going to define a coefficients variable as a data frame of the GWR results. And we're just calling columns 2 to 6, which is going to be our beta coefficients. But to plot these, we're going to need to reshape the data. So after we run this, I'll show you what the transformation does. But so basically, we're going to have like a data table. Coefficient is going to be a data table where each row is a GeoID is representing the census tract, and then it's going to have each column is going to be like the beta coefficient for this variable, for the next variable, and so on. We want a data frame with only 2 columns. We just want one column with the census tract and the variable name, and then what the beta coefficient value is for that. So then we can plot that all in the same function. And so what we do for that is we create a new variable and we assign it as the melt function from the reshape package on our coefficients. So we can go ahead and run this code chunk here. And what that's going to output is a bunch of box plots. So for each variable, it's the distribution of the beta coefficient across all of the census tracts. And so what we can see here is there's a lot of variance in the beta coefficients, where basically we're seeing the relationship in the regression coefficient change between census tracts from negative to positive. So this is really indicating to us very high spatial variance. And before we go forward, we can look in the global environment again to kind of see what this melt function is doing. So our coefficients, which is up here, if we open it, we can see this is what it looks like normally. So we have each row represents a census tract, and then we just have like each column represents the beta coefficient for that variable. After we do the melt function, so our new variable melt coefficients, we can see now that each row is still representing a census tract, but basically the data frame is transformed into just two columns. So we'll have like the average release for each year and the beta coefficient for it for that census tract, and then it's basically stacked now instead of spread out. So we go, starting with our exposure and then theme 1 and theme 2. And we do this so we can pass it to our plotting function, because basically the box plotting function in R, it doesn't know to like which column to look for. It can only take two columns, like our variable name and then what the value is for that. And so again, we can see there's a lot of variance going on. And to get a better idea of how this variance is spatially distributed, we're going to map the beta coefficients. So we do this starting on line 544. Basically, we're going to create a bunch of plots using a custom plotting function that's going to it's going to create maps of all the census tracts in Colorado, a separate map for each variable, and it's going to shade in those census tracts based on what the value of the beta coefficient is. So we can run this code chunk here. And so this one will take a little bit more time because it's more graphically intensive. You might see some messages in the console as it's working through it. You'll know it's done when some stuff shows up under the code chunk. And then again, you get that right arrow here with the empty cursor. But so we can just wait and let that run. It should take about a minute. Okay, so we know it's done because we have our arrow with our empty cursor. And then now we can see our output from that. So again, I'm going to save this image. I'm just going to rename it to 12. It'll show up down here. And then now we can see the maps that it's outputting. So for every variable, it's mapping the census tracts of Colorado, and it's shading those tracts based on what the beta coefficient is. And so there's a few things we can see from this. Basically, the gray areas are where we're not seeing a significant relationship at all. So in large parts of the state of Colorado, for different variables, we're not seeing a significant relationship. We're seeing a lot of spatial variance. This can really be seen if we look at RPL theme 3. I'll zoom in a lot more here so you guys can see it easier. So most of the state for this variable, we're not seeing a significant relationship with low weight births. But in areas where we are seeing a significant relationship, we're seeing very high spatial variance. So like the census tracts north of the Denver area, we're seeing a negative relationship with this variable. And then in areas east of Denver, we're seeing a positive relationship. So this is really indicating to us that there's still spatial variance, lurking spatial variance that the GWR is not capturing. And then one more thing we can look at is starting on line 571, we can map the local R-squareds. So we're going to just create a single map of the state of Colorado where each census tract is shaded based on the R-squared value for the local regression in that census tract. So you can run this code function. And then so you can see it's outputting a map of the local R-squared. And I think this one, yeah, this one let me show the whole thing. So you can really see the variance here. We're basically in like the northeast part of the state, we're seeing significant negative relationships. Basically, where our model's saying based on your explanatory variables, the higher those variables are, we expect to see lower rates of birth weight, lower rates of low weight birth. But then in like the western part of the state, and especially the south central part of the state, we're seeing the opposite relationship. We're seeing a positive, significant relationship, which is what we're expecting. So basically, yeah, this is telling us that the GWR model, it's capturing some of that spatial variance, but it's still not modeling it very well. And so this is where the MGWR comes in. And so we do still have some time, so I can actually go on to the MGWR. And what you guys are going to see is that the MGWR, which has the ability to adjust neighborhood size to model scalar spatial functions, does a much better job than just the base GWR. And so we can go down starting on line 625, we're going to run the MGWR. And so this basically we do similar things. So we don't need to make a new distance matrix or stuff like that. We can call the same ones in that we already created. And so one thing that MGWR does is you can set numbers of iterations. For now, I'm just going to show you it with one iteration. But so this model, it can run over many iterations and optimize itself. And so in the markdown file, which I'll go back and open up for you guys here, we ran the MGWR with it only shows one iteration here. But so we did this with like 100 iterations, and that took about an hour to run. But it creates a slightly better model, a more optimized model. So if you were actually doing this for like a real study, you'd probably want to do more than one iteration. But we'll just do one iteration here for now, so things go a little bit faster. So we can start and run this code chunk. And so as you can see, the MGWR is running, and it's adjusting the neighborhood size dynamically to try to better capture those spatial relationships. And so it runs, it outputs a whole bunch of stuff. You have to scroll through a lot because it tells us things when it's going through. But so starting on line 658, we can go do our diagnostics again. So we can run this code chunk to get a clean readout of the R-squared value. And now you can see our adjusted R-squared has gone all the way up to 0.297, which is a significant improvement over the base GWR model. Starting on line 665, we can run look at the residuals again. So things are a little bit tighter, less shooting out from the normal curve. But so we can look at spatial autocorrelation starting on 674. So again, this is going to tell us our residual is spatially autocorrelated. So we can run this code chunk here. And then so now we get the output again. And so what we can see is now our p-value is 0.118. So our Moran's eye test is no longer significant. So this is telling us that our residuals are no longer spatially autocorrelated. And now we can be comfortable with our MGWR model that it's capturing at least a majority of the spatial relationships between the variables. And so starting on 690, we can plot the beta coefficients again and get those box plots. And so now you can see that there's a lot less variance. Basically, almost every single variable except theme 2 is either entirely positive or negative. So we're not seeing that flipping of relationship across the study extent, which is more of what we want. And then so going down to optional step 3 on line 714, we can run our plotting function again to plot the beta coefficients across the study extent. Okay, so it ran. And so for some reason, like on this one, it's showing the whole thing. It's one clunky thing about markdowns in R. I'll save this as an image again so we can zoom in. I'll do this as 13. PNG shows up here. So again, we get our maps, and the first thing you can see is we have a lot more significant relationships across the study extent in individual tracks. And then now we can go look at, say, RPL theme 3, the one that was showing the very high variance where the relationship was changing from positive to negative. And now we can see that throughout all of the census tracts, there is variance in what the relationship is, but it's entirely positive. It's at least either basically insignificant at 0 or going up to 2.5. Now you can go down. So we don't plot the R-squareds here, but we can run this final code chunk, which will basically take the results from our linear model, the normal GWR, MGWR, and put it into this cable function from the knitter package that creates a nice markdown of the outputs from those models. So we can run that. And so I'm on dark theme, and so it's impossible to see. So I'm going to go back to our markdown HTML document. We can go to the end there, zoom in a little bit. And so we can see here, again, basically comparing the results from all of our models. So we can see as we go from the global linear model to the spatial models, our R-squared is improving, especially with the MGWR. And then we can again look at the Moran's eye and see that it is no longer significant with the MGWR. So basically, we can say with this MGWR model that we built, we're confident that we're capturing the spatial relationships accurately. And then now if we were to like go forward and continue this as a real study, we still have a pretty low R-squared. So now we can say, you know, we're capturing spatial relationships well. So we're missing certain covariates that are explaining low weight births that we need to look at. So we go back to the SVI data set, look at maybe more specific variables and find other types of data that might explain low weight births to build a more accurate model. And so, yeah, so basically, through this workshop, we've gone over reading and formatting data in R, running global and local statistics, analyzing model diagnostics, and plotting maps of our model results. And yeah, so that's pretty much the workshop. First, I'd just like to give a special thanks to the Inspires team and the Department of Communications and Journalism. I'll mention this workshop was originally given at the NIEHS PH meeting in February. I co-created this workshop with my colleague, Dr. Daniel Bean, so special thanks to them, and our advisors, Dr. Ian Lin and Dr. Joseph Hoover. And besides Inspires, the content of this workshop is also supported by the UNM Metal Superfund Research Program Center and the UNM Center for Native Environmental Health Equity Research. And I'll just put up my contact info so you can feel free to reach out to me with any questions or anything like that. We're going to be providing these slides and all the data used in this workshop. And also I have just my personal website on there. And so on my website, you can also see this workshop again. If you just go to this link, RGIS workshop, it opens that markdown file so you can easily reference it. Then I have a link to the GitHub repository that you can find with all the data on there too. If you go to just the repositories on my page, it's that Inspire Spatial Reg workshop where you can find all the data and everything. And I'll push the slides to this too so you guys can reference those again.